Good evening, everyone. I am Arko. Let me welcome you to the week 9 live discussion session of the course, NPTEL course, Molecular Spectroscopy, Physical Chemist Perspective. So, as we are doing for the previous 8 weeks, we will discuss some of the topics that has been discussed in the online lectures, and then we are trying to solve the previous week assignment, and I have a few numerical problems related to the IR spectroscopy that we will try to solve together. Okay, then let us start. Let me share my screen. I hope you can see my screen. So again, welcome to the week 9 live session, and our objective will be to doubt clear, as no one is here. If someone comes, we'll ask for the doubts, and if not, we'll try to cover a few topics, and we'll do the weekly assignment solution. And these sessions will be recorded, as you understand, and I hope you are seeing this thing on YouTube, and hope it will help you to solve a few problems. So let us actually, in the previous week we have discussed the week 8 topics and week 9 topics. So let us start with the week 9 assignment today. So the first question, that according to the Born-Oppenheimer approximation, so what is true, that we have to comment about the psi as well as the energy E, as the means the wave function and the energy. So here the Born-Oppenheimer approximation tells us that firstly, what do Born-Oppenheimer approximation tells us, that the energy E, so there are a lot of energies, right? It means what I am trying to say, there are electrical energy, right? Electronic energy states, energy, vibrational energy, and we have, what else we have discussed, rotational energy, right? So these all are actually, according to the Born-Oppenheimer approximation, these are all we can treat them separately, and this is obviously an approximation. In some cases you will see the breakdown of this Born-Oppenheimer as well, right? So accordingly to that, so actually the psi will be product of all these wave function, electronic states, vibronic and the rotational one. So this is the second option, is a correct option. And the energy, so this you have, I think, solved if you have done the quantum mechanics course or quantum chemistry courses, you have solved for 2D particle or separation of variables, right? There you have assumed your psi to be where there are multi dimensions are involved, you have assumed your psi to be a product of individual wave functions. So here also we are doing the same, and the energy to be the sum of that. So these 2 and 3 are the correct options. Okay. Now for the second question, for a molecule where the equilibrium bond length of the excited state is greater than in the ground state, it is necessary that the Frank-Condon factor is not maximum for the transition. So first, what is a Frank-Condon factor? So when we actually discuss this transition moment integral, right, TMI, there actually you will get this term, psi v dash psi v. You can term is at v double prime also. So here it means that this is the excited vibronic state, and this is the vibronic state from a ground electronic state, and this is from the first excited electronic state. So this is actually, and there are a lot of factors, right? Orbital function is there, that is psi n e, and then your dipole moment psi e dash, psi e double dash, but double dash means the ground state, and also you have your spin part associated with this psi as double dash. So this is actually a Frank-Condon principle, Frank-Condon factor, which actually decide your intensity of the transition. So actually what I'm trying to say, suppose this is your excited state and this is your ground state. This actually means, so the x-axis is actually your separation. You can do this as a reaction coordinate. Mostly in this Morse curve, what we are discussing, this is as a bond length. Okay, bond length as your reaction coordinate, and here is your energy E. Energy is increasing this side. So this is your ground state, and this is your excited state, and then there is some vibronic states are associated like this, right? Okay. So now the drawing I have drawn, actually that means actually the ground excited state has lesser bond length than the ground state. What actually in the question it is being asked that what will happen if the excited state bond length is greater than the ground state, then your Morse curve will look something like that, right? So here your excited state bond length is more. So then actually what generally happens in when there is no difference in the bond length, you will expect a 0 to 0 vibronic, the 0 to 0 electronic transition to be expected, a more overlap between this wave function, vibronic wave function, and more intense transition. But in this case, when the equilibrium bond length is not equals to that of the ground state, of the excited state, then what will happen that your 0 to 0 transition actually is not going to be the maximum, right here. So actually your this 0 to 0 dash transition is not going to be means for this the Frank quantum factor is not going to be maximum. Other thing can happen, from 0 it can go to something 0 to it can go to 4, 5, something, anything else than the 0, right? So it is the maximum. Now the question number 3 says the dt transition are forbidden by, this is you already know, this is so from here you understand that dt means that they are talking of the orbital, not the spin or the Frank quantum factor. So actually your dt transition is forbidden by orbital selection, which is actually a Laporte selection, right? Okay. Now question number 4. For a molecule, these things are given. So I hope you remember this curve. Let me draw this again. The same thing. These are the electronic states. So we are assuming there is no change actually. So this is again your energy, and this is your reaction coordinate. That is here bond length. Right. So this is your fast v equals to 0, and this is your v dash is equal to 0, right? And up to this point, after this there is a continuum, because your excited state molecule will get separated into the atom, right? So this is actually your dissociation energy at the excited state. What about the ground state? Ground state, after this energy it will get dissociated into atoms, right, in ground state. So this is your D0. Now for a electronic transition in the band origin, we means V is equal to 0 to V naught is equal to 0. This energy gives by your band origin, energy is 0 to 0. And one more thing is that suppose your already your atoms are dissociated in the ground state itself, and then you can add some energy to it, so it will reach to its dissociated excited state form. That is your epsilon Ex. I write it like this. So from here actually what from the energetics you are getting the relationship, that is your band origin plus your dissociation energy at the excited state is going to be equal to that of the dissociation energy in the ground state plus the dissociation energy the excitation energy of this dissociated product. So that is your epsilon Ex. Okay, so we have to, from this question, the question is that for a molecule the area under the curve for Barge-Spuner explanation. So the Barge-Spuner explanation is actually nothing but this is nu, and your this is actually this delta EV, and this area under the Barge-Spuner plot actually give you nothing but the excited state dissociation energy, that is d naught, that is given as your 5000 centimeter inverse, right? and the dissociation energy for the molecule in its electronic ground state is given, that is your D0, that is given is 8000 centimeter inverse. And what is another thing is given, the excitation energy of the dissociation product is 14,000 centimeter inverse, so that is also given. So this is epsilon Ex is also given 14,000 centimeter inverse. So it is very easy to calculate your band origin. That will be nothing but this D0 at ground state plus this epsilon Ex minus your excited state dissociation energy. It will give you around 17,000 centimeter inverse. So actually your correct answer is second. Okay. Now let's get us back to the question number 5. I hope this is question number 4 is clear. Now question number 5 says the bond length of the homonuclear diatomic molecules can be determined with the help of both. So as you know that from vibrational spectroscopy we are not going to get properly, right? From the rotational Raman, you remember there is delta J equals to delta J was plus minus 2, right? The selection route for rotational Raman. From there also you get a relationship between the rotational constant and something your energy, right? So from there you will get the rotational constant, and from there you can get the length of the homonuclear diatomic, right? So you can get it from the rotational Raman as well as from the electronic spectroscopy. And now a very important question, that the normal mode of vibration for POCl3R. Now how does a POCl3 looks like? So POCl3 actually looks like a pyramidal one, or the point group you can say is C3V. C3V is the point group. So let me get the point character table for the C3V. So I'll get it from here. Okay, I think the net is not that much good, I guess. Acha, it's here. So I'll copy paste it and paste it here, so that we will discuss. Let me go to the next page and then discuss. I hope this is visible to you. Now see, in earlier week what we are trying to see, that suppose POCl3, right? So we are what we are checking, that normal modes of vibration, whatever is given, suppose we are calculating it from the number of atoms, something like that, right? So here the number of atoms are, how many number of atoms are there? 1, 2, 3, 4, 5. So how many degrees of total number of degrees of freedom? That is 15, right? Now this is a non-linear molecule. Then how many normal modes of vibration will be there? 15 minus 6, right? That is 9. Now the problem is, see, in the earlier week what we are trying to see, that how many modes are there, normal modes, by total of that, and we are getting the answer. But now see, here it is 2 into 2, 4 and 7. So here it says 7 modes of normal modes of vibration, right? So it's not a correct answer, right? Now the second option says 3 and 3 into 2, 6. That means the total number 9. So it could be possibly a correct answer. And what about this A1 and 4E? It also says 9 modes of vibration, normal modes of vibration. What about the third option? It says 6 and 2, 8. 8, right? 8 is not a right number. That what we are calculating from 9. But we don't know if option B or C is correct. Now we have to go to that method what we are doing earlier yesterday. That is your, suppose this is your POCl3. Now we will see how many of these atoms are not changed due to this operations, right? So if we operate identity operation, we will see that all 5 are remaining at their place, right? All 5. Okay. Now what about C3Z? So if we perform 1 times C3Z, only if you see that P and O, these 2 atoms will remain its place, so other will change its place, right? So 2 will be unchanged. What about 3 sigma V? So when you are talking about these molecular planes, you will see that O, P and Cl, these will remain at its place, and these 2 Cls will going to change their place. So 3 atoms are going to be unchanged. Now what we have learned, that your total degrees of freedom of those modes, you will get n into gamma xyz. Now before that you need to know what is gamma xyz, right? So what is your gamma xyz here? So xy both belongs to this 2-dimensional representation, that is E, and together, and z belongs to A1, totally symmetric representation, right? Now so we'll take a sum of that, of the characters, and we'll see what gamma xyz belongs to, what it will give us, a reducible representation that will give us 3, 1 minus 1, that is 0, and then 0 plus 1, that will give us 1, right? Now we'll get this n into gamma xyz, so we will get 15 and 0 and 3. Firstly, we are taking the number of atoms that are unmoved, because we have already seen that if your atoms moved during any symmetry operation, it's from the transformational matrix, it's actually diagonal elements become 0, and non-zero elements goes to the off diagonal place. So your character will have no contribution from that. So that is why we are taking the atoms which are unchanged. Now from here, what we know, that your gamma V vibrational modes will be your total, this n into gamma xyz minus your gamma xyz, which will come from the translational motions, and your gamma rod, right? Rotational, whatever the vibrational things there. So from here we will see that gamma, your rod is gamma rotational is, see this Rz is here, and Rx, Ry are forming to E. So we are also going to get this as 3, this again as 0, and this as minus 1. So we will deduct it from this thing, n into gamma xyz, this gamma xyz and gamma rotational, and we will see what we are getting. So we have, firstly we are getting 15 minus 6, that is 9, right? And then what we are getting, 15 minus 6, that is 9, then we are getting 0, and then we are getting 3. Now we need to check this gamma vibrational, what is the reducible, by how we can, means we already know, right, that if your gamma reducible is suppose this is ai gamma I and summation over I, so your ai is nothing but 1h, h is your order of that point group, and your sum over I, not I but R, your chi of is the character of that from the irreducible representation, and from that of the reducible representation, the characters. So we will do the same here. So how many numbers of A1 is going to be there, that we will check. So that here the order is 6, right? H is 6 for C3b, so it will be 1 by 6, and then we are going to get this. And remember, the total number of operation is actually, there are 2 C2s, 2 C3s, so we also have to multiply here also. So 1 into 1, that is the character from the A1 for E, and reducible, it is 9, right? Now next is we don't really bother because it is 0 will be there, so let us not bother about C3. And what about 3CV? There we have 3 operations, right? 3 sigma v operations, then we have 1 the character and 3 from the character of that reducible representation, and we will get something from here, I guess 1 by 6. 9 plus 9, that is 18. We will get 3a1. And what about a2? N of a2, how many a2 will be there? 1 by 6. Similarly, we will get 1 into 9 here, then we will get something 0 here, and then we have 3 into minus 1 character from the a2 of sigma v, and then we have multiplied with that of the character of the reducible, and we will get 0. And what about ne? How many e are there in the reducible representation? That is going to be 1 into 2 into actually 9 plus 0 and 0, because 3 into 0 into 3, right? So here actually you are also getting 3, so your actually gamma A is nothing but gamma actually 3a1 plus 3a. So actually your second option is the correct option, right? This, not this. This is a wrong answer, and these two obviously. Okay. Now we'll go to the discussion. We'll do the discussion about the whatever is being discussed in the week 10 lecture series. Okay. So we'll quickly do that. So in week 10, lecture number 49, actually we have discussed about rotational spine spectrum, how it is arriving. It will actually arrive, actually your energy is nothing but, right? So first, the rotational selection rule will be delta J equals to plus minus for all, and now for singlet to singlet, transition, you will see your delta J will be, firstly your TMI you already know, right? TMI is psi v dash psi v. Now your psi orbital part psi e dash psi e, and multiplied by your spin part, spin selection part. Now for delta J for singlet to singlet, it will be 0 and plus minus 1, and not 0 will not be favorable when J equals to 0, J double dash is equal to 0 to J dash is equal to 0, okay, for not for this transition. So this is not allowed. So now with this thing background in mind, so what is the difference, what we will see? So actually what we are going to see is delta E is nothing but your firstly there your electronic energy is there from the electronic state and the vibronic state, and then suppose your rotational constants are different, actually what you are going to see your delta B J into J plus 1, right? This is what is expected, because we are expecting that with changing the electronic state, your rotational constant will vary, right? The rotational constant will change. So what we are actually going to see that is delta B is going to be new, this part will be unchanged, EV plus, suppose we will first get from your excited state, that is B dash J dash plus 1 minus B double dash, okay, B double dash and J double dash plus 1. J and J prime and J double prime belongs to the ground state, and J prime belongs to the excited state, electronic state, and J prime and J can go from 0 to 1, right? Okay. Now what it is actually going to give us, EV plus it is going to give us, so let us plus check for delta J equals to plus 1, right? That is your R branch. So will be b dash, and let us not go into that. And so your j prime minus j double prime is actually 1, and j can be written as j prime plus 1, right? So we are getting something like j prime plus 1 and j prime plus 2. Here you are not changing anything, right? I'll just do the calculation. Let us see what we are going to get. Now here your j prime square is there, and as well as you are going to get b prime 2j 3j plus 2 bj square plus j, right? Something like this. So from here you are going to get new ev plus b dash minus b double dash, right? If you take common the j prime square, now what else you are going to get? Am I making any mistake here? How am I going to get? Acha. So let me take this in terms of j prime only, right? J prime. So your j prime is, so your actually j double prime is going to be j prime minus 1. So I'll just erase this part and I will rewrite. I'll erase this whole part. Just wait for me. I'll write this in terms of the j prime only. So this will become j prime minus 1, and this will become j prime. So you are going to get something in terms of, so your j dash square or j prime square will be, and in bracket it will be b dash minus b double prime, right? And here for j dash we are getting b prime from this side, and from here we are going to get something in plus, that is b plus and b double prime, minus minus plus. Okay, and similarly you can see that for delta j equals to minus 1 you are going to get p branch, right? And there you will have your j prime as j prime minus j double prime equals to minus 1, and actually your j prime you can write it in terms of j double prime minus 1, and from here you are going to actually get delta E nu bar EV plus b prime j double prime j prime plus 1 minus, let I am writing it another time. Now I will replace the things. Right? Now I think we will be on the same page. Now I will take a minus j prime, j double prime actually. Here we will get something b dash plus b double prime, b prime plus b double prime. So in terms of j prime or j double prime, what we are actually getting is some rotational fine spectra, and Sarah has shown that for p branch and q branch, q is where your delta j equals to actually 0, right? So your it will become delta e new ev, it will actually become the same thing, right? So b prime, now all are same except b dash minus b double prime. All the other things are same, or in terms of j prime you also can see. So for p and q branch, it was discussed that with increasing j value, the space will be widen up, and for r actually you are going to see something like this, a parabola, and in case of p and q you are going to get a half parabola. The negative part you won't get, and for a q for a r branch you are going to get something like this, okay? And this is also known as band head. So I will discuss a little bit about that. So what you are actually getting is so for p or r branch, you are what you are getting is new AV b dash plus b double dash p plus this p is nothing. This is a suppose this is your j or j bar, okay, nothing else. It's like the aim we took for the vibrational rotational fine structure there, right? So this has a square term is always positive, right? But this, depending on this p, it will change. So, and for this band head, what you are actually, so this is your actually this is your energy scale, and this is actually your p, right? So for a this case you need to get a inflation point where the slope is 0. You will get by this dp. So this first term will give us 0 plus b dash plus b double dash. The second will get 2 b dash minus b double dash p, and it will be equals to 0, right, for a maxima. And so here we will get the here for this particular p, so this is not 0. So for this particular p we will get a band head. So for this particular we will see which p max or which value of p we are going to get that, and there this change is d nu r by p is actually the slope is 0. So you will see that p is going to be actually b dash plus b double dash by 2 b double dash minus b dash, okay? From here also, from a nearest integer value we will get this. So these kind of numerical problems can also come in the question. Now the next thing we are going to discuss, that is the week 51, that is the symmetry of the electronic states. Here what we will learn, that if suppose you have a molecular orbital, that is your psi, which is actually your phi 1, phi 2, phi 3 and other things, right? So actually the symmetry of your psi is going to be actually the multiplying of this thing also. And it will go. Now there are 4 rules that mentioned in the class, right? One, suppose your molecular orbital is fully occupied, right, or doubly occupied. So one molecular orbital can have 2 electrons, right? So W occupied MO actually will give you a totally symmetric, right? Because so it will give you a totally symmetric representation. So it will not take part, means you can say only the core will not take part, or only the valence orbitals or the valence orbitals are going to take part in this case. Others it will be totally symmetric and it will be 1. You can think of it as 1. Okay. Because you have seen, right? Suppose this is your suppose you have sigma 1s, there you have 2. Now your sigma 1s suppose suppose be 2u, and sigma 1s2 means you have to multiply it twice, b2u into b2u. Obviously you are going to get something as, here you are going to get something totally symmetric, right? This thing you have to learn. Okay. Now the second point says, if it is a doubly occupied by demo, then the symmetry of the state will itself will be the symmetry of individual MOs, or symmetry of the MO, the symmetry of the state. And the third rule says, when suppose you have 2 non-degenerate energy or 2 non-degenerate orbital, 2 electrons in 2 non-degenerate, suppose something like this. Okay, so in these cases, if 2 electrons in 2 non-degenerate orbitals or 2 non-degenerate MOs, then for the state, symmetry of the state will be, we have to take the direct product of these MOs. Okay. Now the case will be difficult, not difficult in this case. Suppose now the next thing is not difficult actually. Suppose you have only one field of thing and nothing else, then your symmetry of that state will be the symmetry of this MO, right? I hope that is not a difficult one to guess. Now the problem will come when we will see that for O2 the pi stars are singly filled. These are actually pi g. These are pi g, and these are actually pi star orbitals, right? So for this in class, it has been deduced. The electronic states are being deduced. How it was deduced? That so both are in pi g, right? So your symmetry of the state will be pi g into pi g. So from product table or from there you can for a O2 it actually belongs to d sigma d infinity h point group, and from there you will see it has been also shown in the class that you are going to get states, electronic states like sigma g plus, sigma g minus, and delta g. Now the one interesting thing is that you can have singlet or triplet in all the cases, right? Because there are 2 unpaired electrons. There won't be a doublet or quadruplet, right? Only singlet and triplet can be there according to their spin. Now it can be either singlet or triplet. Now if you see, you have two electrons, or actually you have 4 space, means 2 orbital 4 space. You can only have only 6 arrangements. You will have 2 electrons, 4 space, right? So you are going to get 6 arrangement, and so you are going to actually going to have 6 states, not 16. From here, if you see, if one sigma g plus and triplet 3 triplet sigma g plus, then it means total of 4, and then again from 4 here, and 2 and 6, so a total number of, I guess, 8 and 8, 16 number of states are possible, but eventually, but you are going to get actually the 6, others are not allowed. So from Pauli's exclusion principle or the antisymmetry principle, you can understand which one will be allowed and which will be there and which won't be there, okay, which electronic state. Now if you see your sigma g plus, this actually a specially totally symmetry representation, okay, totally symmetry, so the special part. So to get the special and symmetric, the product of that to be antisymmetric, you want your spin to be antisymmetric, and antisymmetric spin part is there only for singlet, okay. And so the triplet sigma g plus will not be there. Similarly, for sigma g minus is actually antisymmetric, okay, with respect to the interchange. You have to interchange the electrons, right? So when you do that, you will see that your sigma g minus is actually antisymmetric special part it has. So actually your spin part will be a symmetric, and that will only be a triplet one. So there will be 3 states. So 1 and 3, 4, total 4 number spaces states are coming from here. So only singlet delta G will be there, not the 3. So this will not be there. One singlet delta G will be there. So what are the states available for O2? In so in ground state it will be available 1 sigma G plus, triplet sigma G minus, and singlet delta G. Now what is the energy scale? So that has been shown, that energy scale by the Hund's rule. You know the triplet will be in the lower one, 3G minus, and then from the multiplicity delta G is there, and 1 sigma G plus is here. Similarly, for this is for a D infinity H. Now for benzene, it has also the electronic states are discussed, where the point of view is D6H, right? So for the pi electronics, electronic states are look something like this, where in the ground state only these bonding orbitals are filled. These are ABMOs, pi bonding molecular orbitals to be specific. So these are filled. So in ground state you will see you are having something symmetry of ground state. The ground state is having a symmetry of and the symmetry of these electronic states, or the molecular orbitals are actually, molecular orbital is E1G for these two, and for these actually A2U, right? A2U, and here also you are going to get E2U, and here you have B2G. These are the symmetry of the molecular orbitals. So for ground state the state is your A2U2 and E1G to the power 4, and this is actually you are going to get a totally symmetric, right? A1G for this. And for the excited state electronic configuration will be there, something like that. One will go here, right? So this is A2U2, so this doesn't really bother us. A1G3 and E2U1. So from here actually when you see, so your so they are actually to non-degenerate through electrons into non-degenerate orbitals, right? Molecular orbitals. So now the state will be E1G into E2U, and from the product table it has been found that you are going to get B1U plus B2U plus E1U, something like that. Now it can be triplet, singlet, that up to you. Not up to you means that we have to need to check, but the states are going to be like that, and the spin multiplicity is made different. Now from there, actually till now you have seen that A1G to, I think, E1U was totally allowed, means allowed spin as well as orbital. But for the A1G to B1U or B2U, actually are spin allowed, not nothing. You have to also mention the spin multiplicity, the singlet 1U and 1 this A1G spin allowed, but orbital. Still you know that using the vibronic coupling, so that has been taught in the last couple of the lectures, where you have understand that even if your so this is your TMI, right? Actually your S, this is the spin forbidden part, a spin part, and this is actually your EV. Right now I am not separating the electronic states from the vibronic state. As you have understand, this will come from when Braun-Oppenheimer approximation failed or breakdown, you can say. Failed is not a good term, breakdown. Then you can see that if your you have already learned this thing, that's why I am not going too far. That due to some vibronic psi equals to 0, v equals to 0 to psi v equals to 1, depends what is actually your symmetry of the v1 or symmetry of the v0. You will get to understand that for that also your even if your that is orbital forbidden, you will have some transition there due to your vibronic coupling. So that you have already learned in that lectures. So I will not go deep into that. But next, what we will try to do, will solve some questions, numerical problems, which we already have done for a few questions we already have done. So what I am going to do, I'll start from here, where we have last solved this question, and then we'll go ahead. Now the question, these are for infrared spectroscopy numericals. The first question is, estimate using the data table 3.4 the vibrational wave number of this A, B, C, D. So we will take help from this table. So for A, we need to get the vibrational wave number for CD. What we already have, CH, right? That is 1300 centimeter inverse. What is the reduced mass here? That is nothing but so why I am taking reduced mass? So actually your vibrational frequency is, or the wave number is nothing but 1 by 2 pi c, your force constant by your reduced mass. So your force constant and other thing will be constant, your mu will change, right? So what is mu CH? CH is, in AO mu we will only discuss C12 and H is 1, so 12 by 13 AMU. And what about your mu of reduced mass of CD? this bond, it will be 12 into 2, that is 24 by actually 12 plus 2, that is 14 mm, right? So your omega CH is already there, right? That is 1300 centimeter inverse, and you need omega CD bar. So let us take a ratio of this. So the expected thing is 1 by 2 pi c. 2 pi c are gone, k will go. So for CD, you should expect mu of CH to be here, reduced much, and mu of CD to be here, right? And which is nothing but, let us see, CH is 12 by 13, AMU will cut, and here it will be 14 by 24. That is your 12 into 2, 2 into 7, that is 7. So your this frequency is nothing but your 13 and 3300 centimeter inverse into root over 7 by 13. So let me calculate that for you. Root over 7 by 13 into 1300, 3300. That will give us actually something around 20 or 22 centimeter inverse. Now we'll perform the same for B, right? So that is OD, we need to calculate. What is the mu of OD? That is 32 by 18 AMU, and we already have for OH, right? So what is the OH reduced mass? OH is 17 or 16 by 17 AMU. Okay, now your this OH vibrational frequency will be multiplied by this, OD will be multiplied by this into your mu of OH by mu of OD. So mu of OH is, we know, that is 3600 centimeter inverse into root over of 16 by 17 into 18 by 32. 9 by 17. So we'll check what is coming there. 9 by 17 into 36. We are getting something approximately around 2619, something like this centimeters. So you have understood, right? So your mu is increasing, so your vibrational frequency is decreasing, right? So for CH it was 3300, and now you are getting for CD, you are getting 2422, right? 2422. And similarly the change is even more, I guess, for OH, OD from OH. Now for the next one, I think, okay. Acha, so now the C is, where is my cursor? Okay, now let me erase that part. Now see, for C you need to do the same for CS. Now your C double bond S is there, but we will take something like we will take an example from 1100. This we can also take what we can do, we can take an example from CF actually, right? Or what do you say? What else is there? CI, something like that. So from there you will get your CS, and you already know for CF, so try to calculate that, you will, I think this will be a, you will be able to do that. the next. So the vibrational frequency of 1H 35Cl is given as 2990.6 centimeter inverse. Second question, 3.7. So this is already given, and without calculating the bond force constant, estimate the frequency for 1H 37Cl, 2D 35Cl and 2D 37Cl. So we don't have to, we already know the vibrational frequency is your nothing but 1 by 2 pi c k by mu. K is the force constant. So what is mu for 1H 35Cl? So it is nothing but 35 by 36 AMA. What is reduced mass for 1H 37Cl? 37 by 38 AMA. What is the reduced mass for 2D, the deuterium, and 35Cl? It is 70 by 37. And what is the reduced mass for deuterium and 37Cl? This, right? So you know that for W by 1H 35Cl, we already know this is 2990.6 centimeter inverse. That is equals to 1 by 2 pi c is there, and k by mu is also there. Mu of 1H 35Cl. And here the approximation is that if you are also changing the atoms or the isotopes, there is no change in the force constant. So that is an approximation. Okay. So under that approximation we are solving this problem. Let us do that. So we don't know, so we know, so without calculating the bond force constant. Okay. So the similar thing we will do for the 1H 37Cl. It will be this of 1H 35Cl into root over mu of 1H 37Cl, or sorry 35Cl, yes, by reduced mass of 1H 37Cl. So this will be 2990.6 centimeter inverse into 35 by 36 AMU, right, into 1H 37Cl 38 by 37, something like this. So let us see how much we will get. We will get 35 into 38. I have done some mistake, I guess. No, 35 into 38 divided by 36 and 37, multiplying by 2990.6. So we are expecting a 298.35 centimeter, something around that. So see, the change is not much, right? The change is not much. 2990 to 2988. Now what will happen, because there is not much change in the reduced mass, what will happen for deuterium 35Cl? It will be same, 35Cl into this mu 2 deuterium 35Cl by reduced mass of 1H 35C, right? So we are going to get 2990.6 centimeter inverse into 35 by 36. Anyway, we are going to get, now we will get something around 37 by 70. 35, 37 cancel. So you are going to get something around 37 divided by 72. Right? 2143.8, or we can say 2144. What will be the vibrational frequency for 2D, the deuterium 37 here? 2990, similar thing, right? 35 by 36 into 39 by 74. Okay, so 35 into 39 divided by 36. It will be even less, 2141. So we are getting 2141. So from this you are getting an idea how to solve these problems without calculating the bond force constant, something like that. And also the idea is pretty clear that when the reduced mass is going to increase due to the change in the isotopes, your vibrational frequency is going to drop down, right? I think same happened with the rotational constant, if you remember, right? Okay. Now for question number 3.9, we will solve this. Assume the data for the molecule 1H 35Cl, the bond length is 127.5 picometer and bond force constant is given. Okay, so what we have? We have R, we have the force constant K. Now atomic masses are given. We need to calculate the 0 point energy. What is a 0 point energy? So that is half this oscillation, right? Centimeter inverse. But first we need to get what is that. So that will get from omega oscillation is 1 by 2 pi c, right? K by mu. Now your mu 1H 35Cl, we already know 35 by 36 A mu, that is 35 by 36 into 1.66 into 10 to the power minus 27 kg. That is nothing but 1.614 into 10 to the minus 27 kg. Okay, so we got the mu, we got K, we have this. So let us see what is the vibrational frequency. So 1 by 2 into 3.14 into C is 3 into 10 to the power 10 centimeter per second. Here we are getting K as Newton meter, right? Newton per meter, 516 Newton meter inverse. And from here we have the mu as 1.614 into 10 to the minus 27 kg, and Newton is your force, that is your kg meter second square. So Newton meter inverse is nothing but kg second minus 2. So your kg will cancel and your second minus 2 will remain inside the square root, and let us see what will happen outside. Okay, so let me do the calculation and get back to you after the calculation. 1.3.14 divided by 3 divided by 10 to the power 10 into 516 divided by 1.614 divided by 10 to the power minus 27 kg, right? I will end this bracket. I will have the 0.5. I think we are going to get like 3001.2 centimeter inverse. Let me quickly cross check with my earlier calculation if I am getting the similar thing. Fundamental vibration, what we are actually W nu 0 or nu is so we are getting something like 3001.2. okay, no, that is not the fundamental vibration, right? Fundamental vibration will come. So this is the 0 point energy. Now from here, what can we have? Okay, now okay, that we have. Now our 0 point energy will be half of this, right? Something around 1500.6 centimeter inverse. I don't know if I am making any mistake. I'm just checking the answers. Yeah, almost close to that. The answer given is 1495.7, or we are getting 1500 something. Okay, and the fundamental vibration is your this one. Actually, this is actually your fundamental vibration for this case, because that XC and those values are not given, right? So calculate rotational constant B. That is also easy, right? B is what? 8 by 8 pi square square IC, 8 pi square IC, 8 pi square IC, right? I think I have done the same thing. I is nothing but your mu r square, right? So from we all know all mu, all this term we know, right? So let us do that. 6.626 into 10 to the power minus 34 joule second. Right? Now in between we have 8 into 3.14 square, and then mu we know 1.614 into 10 to the power minus 27 kg, right? And what what else do we have? R square. R square is given in 127.5 square. This is in picometer. In meter it is 10 to the power minus 12, right? Meter square. Okay, into C. C I will take in centimeter because I will eventually need the centimeter inverse, right? So joule second is Newton meter second. Newton meter I shown you earlier that it is kg meter second minus 2. So it is nothing but kg meter square second minus 1. We are going to get from here. So now the kg will cut, meter square cut, second inverse cut. So centimeter will come here and centimeter inverse. Okay. Just tell them I'm still here. Okay. Okay. Now let me do the calculations and then I am giving you the value. So the first is 6.626 into 10 to the power minus 34 divided by 8 divided by 3.14 square divided by 1.614 divided by 10 to the power minus 27, now divided by 127.5 whole square divided by 10 to the power minus actually 24 divided by 3 divided by 10 to the power 10. So you are getting something around 10.67 centimeter inverse, right? So we have calculated A and B, right? This and this. Now calculate the wave numbers for the lines P1, P2, P3, R0, R1, R2. So what are these? P branch and R branch, right? So this is coming from the rotational fine structure. So I will go to the next page. So means actually they want this. So this is your V is equal to 1 and this is your V equals to 0. These are your rotational lines, right? So you won't get the band origin, but here from here you will get to 0 to 1. 0 1 to 2 rotational lines. So this is something. This is your here your delta J equals to plus 1. So this is your R branch. Okay, and your P branch is from here you are going to here. Now next you are going to 3 to 2. Now next you are going to actually you are going from 3, not here, 3 to 4 to 3. Here your delta J equals to minus 1. So this is actually your P branch. And you won't expect anything at the band origin, right? Here your W0 should be there, but you won't see that, but you know the calculation, right? So actually your new P or R is actually nothing but new P. Let me go with the P first. Your band origin minus 2 into B, your rotational constant will be there obviously, J bar plus 1, right, for P. Now you can vary your J bar from 0, 1, 2, 3. So for this J equals to 1, so B you already know 10.67, right, centimeter inverse. This you know your 3001 point something, right? How much? We got 3001.2 centimeter inverse. For J equals to 0, you will get nu bar P of 1. Nu bar P of 2 you will get, and you will get W0 to be, so P1 you want J double dash to be 0, here you want J double dash to be 1, P3 you want your J double dash to be 3. Now for new R, same R0, it known as R0 because it is starting from Z equals to 0 actually. Okay, I think I am making one mistake. I'll just quickly check. Okay, no mistake. R equals to 0. Same thing here, your thing will change, that plus 2b J double prime plus 1. Still let me check once. Okay, so for P branch you have minus 2b J, actually your, here I have made one mistake, it should be J prime and here also J prime, this should be J prime, and for this it should be plus 2b J double prime plus 1. So this plus 1 is actually making the factor, and for R equals to R0, R0 you will say J bar equals to 0, R1 you put J double prime to be 1, R2 same you put J bar to be this 2, and you will get the wave numbers, right? You can do that. Now you can sketch that P1, P2, so you expect something like this, right? Something like this. You are going to get this from P branch, and these are coming from R branch. Okay, and what difference? And the fifth question is actually very interesting. It says that suggest two differences which you would expect to find between the spectrum you have sketched in D and that actually observed in AC. Two things. First, your with increasing J means this. See, so this is, we are taking J equals to 0, this we are taking, so when for the P branch where we are going to take this J prime to be 1, 2, 3 for a lot period, we will see that it will not be a equi-space, the spacings are going to be much higher. And same for the R in opposite thing will happen, they will close up, means the distance will get narrower. And another thing that this is, we are expecting for a particular isotope of chlorine, or you can say deuterium also, but in case of deuterium it is very less. The normal 1H is high, but for Cl, you know, there is 35 and 37 Cl, so that may give arises due to means different peaks also. Means for here we are discussing only about 1H 35 Cl, so you are going to encounter for 1H 37 Cl also. I think the ratio would be something around the abundance of the Cl itself. So 35 Cl will be, if it is 3 times, then it will be 1 time, something like that. So you are going to get something like that. Okay, so and the last question for today, explain why CEO stretching vibration of an aldehyde gives rise to a strong absorption in the infrared, yet absorption due to CC vibration in alkene is normally very weak. So you know, right, for an infrared transition or a vibrational spectroscopy, what you need in a molecule first? The first and foremost important thing is that there should be a dipole moment change due to the oscillations, right? So you understand, right? For the CC vibration, C double bond C, suppose similar substitutions are there. So you can understand that the dipole, there is no dipole change, right? The dipole change will be very weak. It will not be a polar bond. So with change in absorption, with change in oscillation, with oscillation, the change in the absorption dipole moment will be either very less or even zero if the substitutions are all the same of a CC double bond. Of this I am discussing right now. Now that is why that the transition will be transition moment integral and intensity, you understand, absorption for the CC double bond in infrared region will be very weak or even zero. Now for a CO double bond stretching vibration, you understand that the bond is itself polar, and due to the oscillation there will be a larger change in the dipole moment, and that is why that will lead to a strong absorption. Okay, and that's all for I think you have understood, and that's all was there for today's presentation, and I hope you will find it useful for your numerical solves, also for your, if you had any doubt, but as no one has joined, I don't know what is the current and how you are coping up with that. I hope you are able to do that, and I wish you all the very best, and I hope I will meet for the next week with week 10 assignment and week 11 discussion and some other numerical problems if I found from any other books like Atkins and some other books. And if you are going to join, then please bring with some problem. It will be nice to solve them. It's not like that I will be able to solve them all, but I will try both, and we'll have a nice discussion next week hopefully, and we'll stop it here then, and we'll meet you next week. Thank you.